100 years ago this month, 36 years old Albert Einstein stood up in front of the Prussian Academy of Science in Berlin to present a radical new theory of space, time, and gravity, the general theory of relativity. General relativity is a questionably Einstein's masterpiece. A theory which reveals the workings of the universe, the grandest skills, capturing and beautiful line of algebra, everything from why apples fall from trees to the beginning of time and space. Over the last century, these two dishes have thoroughly transformed our understanding of the universe. It takes relativity and quantum mechanics that we learn what the universe is made from, how it began, and how it continues to evolve. The problem with the universe. This is the essential problem. The universe is far in interesting relativities and quantum mechanics appear to suggest that the universe should be a boring place. It should be dark, little, and lifeless. But when we look around us, we see we live in a universe full of interesting stuff, full of stars, planet, trees, squirrels. At the heart of this problem are the numbers, two extremely dangerous numbers. These are probabilities of the universe that we can measure, and they're extremely dangerous because if they were different even by a tiny bit, the universe as we know it would not exist. The first of these numbers is associated with the discovery, the Higgs boson. The Higgs field. The Higgs field is a little bit like a magnetic field, except it has constant value everywhere. It's all around us right now. We can see it or take it, but if we can't there, we would not exist. The Higgs field gives mass to the fundamental particles that we're made from. If it wasn't there, those particles would have no mass, and no atom cools from, and there would be no ice. Dark energy. But there's actually an even worse example of this kind of fine tuning of the distress numbers, dark energy. We don't know what dark energy is, but the best idea is that is the energy of empty space itself, the energy of the vacuum. Now, if you use good old quantum mechanics to work out strong dark energy should be, you get a absolute astonishing result. You find that dark energy should be then the power of 120 times stronger than the value we observe from astronomy. This is a number so mind-blowing you that it's impossible to get your head around. This number is bigger than the numbers astronomy. String theory and multiverse. One of the most promising candidates for a unified theory is string theory, but it has one catastrophic problem. It's turned out that string theory isn't one theory at all, but a whole collection of theories. It's been estimated in fact there on the 500 different versions of string theory. Each one would describe a different universe with different laws of physics. Suddenly, we can understand the widely finite value of these two generous numbers. Suddenly, we can understand the finite value of these two generous numbers. In most of the multiverse, dark energy is so strong that the universe gets torn apart of the Higgs field so weak that not atoms can form. We live in one of the places in the multiverse where the numbers are just right. we live a good luck universe. And conclusion, but if in 2 or 3 years time we have found nothing but the Higgs boson, then we may be interesting a new era in physics and era where there are great because of the universe that we cannot explain, and I where we have hints that we live in a mal universe that lies frustrating forever beyond our reason. I where will never be able to answer the question why is the something rather than nothing. Thank you.